In this second lesson on variable acceleration, we're going to focus on integration instead. So this is the same set of graphs that I had in the last lesson, and we talked about differentiating the distance to get velocity, differentiating velocity to get acceleration. Now we can go the other way, obviously by using integration, because that is the opposite of differentiation. We also know that integration is about finding the area under the graph, which hopefully agrees with what you remember from chapter 9, about the area under a VT graph being the displacement, and the area underneath an acceleration time graph being the velocity. Okay. Now it's a little bit harder to visualize that on here, but if I found the area in this section here, I could plot it like this. So after, say, 0.1 seconds, the area is very, very small, so it's down here. But the area increases linearly. Okay, so as time goes on, this rectangle just gets wider and wider and wider. So the velocity goes up and up and up, so the area is going up and up and up. In this section, there's not actually any area between the line and the axis, and so the total area just stays the same. And now here, this area here is negative because it's below the axis, and so my area begins to decrease until it reaches 0, and then it becomes negative. And then I've got a positive area again here, so then my area starts to increase again. Okay, but in reality, the easiest way to think about this is it is the opposite of differentiation, or it's the area underneath the graph. We also know from lots of problems we did in chapter 9, if I try and find the area under a VT graph, I get the distance, or the displacement. So what we can write is velocity is the integral of acceleration, so I can integrate a with respect to time. And likewise, I can get the displacement as the integral of the velocity with respect to time. So the area under a VT graph gives you displacement, and so on. So we've got an expression here for a particle that's moving along the x-axis. At time t equals 0, so at the start, the particle is at the point x equals 5. So that's its starting position. It doesn't start at the origin, it starts at x equals 5. The velocity of the particle at t seconds, let's just write this down. The velocity is 6t minus t squared. So part A, find an expression for the displacement. Now remember, the displacement is the integral of velocity with respect to time. So I need to integrate this expression here. So it's going to be 3t squared minus 1/3 t cubed plus c. Okay, now the plus c bit, this is the important part. We need to work out this constant of integration using some other information. In pure maths, it would normally be a coordinate. Well, that's essentially what they've given us here. They've told us at time t equals 0, x is 5. So we can substitute that into here. So when t is 0, x is 5. So that would mean that c is 5. So the displacement is 3t squared minus 1/3 t cubed plus 5. Part B, the distance of the particle from its starting point when t is 6. Well, let's plug t equals 6 into our expression for the displacement then. So if I work that out, then I get 41 meters. So that is its displacement from the starting point, it'll be 41 meters. Okay, here's a second example. A particle travels in a straight line. After t seconds, its velocity v is given by 5 minus 3t squared. Find the distance travelled by the particle in the 3rd second of its motion. So this is an interesting bit of wording here. In the 3rd second of its motion. So 0 to 1 is the 1st second of motion. 1 to 2 seconds is the 2nd. second of motion. 2 to 3 is the third second of motion. So we are finding how far has it gone between t equals 2 and t equals 3. Okay. That's what we want to work out in the third second. So to go from velocity to distance, we need to integrate it. And we could actually do this as a definite integral. Maybe if we think about what this graph looks like. So we've got 5 minus 3t squared, or 5 minus 3x squared. Let's write it as. And I want to find the area between t equals 2 and t equals 3. Okay, let's make this graph look a bit more sensible. Okay, so what I want to find is this area. It's actually going to be underneath the axis according to this graph, so it's going to be a negative area between here and here. Okay, this area here with a curved edge on it. So I can do that as a definite integral. So that's going to be the integral of 5 minus 3t squared dt between 3 and 2. Okay, and you can either do that by hand or you could do it on your calculator, but let's just do it by hand here to demonstrate how this works. So this is going to be 5t when I integrate it minus t cubed between 3 and 2. Substitute in your first point. Subtract second point. Then we can calculate each bit. So it's going to be minus 12 minus 10 minus 8, which is 2. So minus 12 minus 2 is minus 14. So it's negative like we expected underneath the graph. The distance travelled is therefore 14 meters in the third second of motion. So you can use a definite integral to help us. But all this is finding the area under a VT graph, just like we did in chapter 9. It's just that here it's a curve rather than a straight line. And so therefore we have to use integration rather than areas of triangles and areas of rectangles and areas of trapeziums. Okay, and this third one. You might already notice my hints that I've written above this question. So a particle is travelling in a straight line. After t seconds, its velocity v is given by 4 minus 2t squared. For t is bigger than 0. Find the distance travelled by the particle in the first 3 seconds of motion. So in the first 3 seconds, so we're looking at the distance covered between t equals 0 and t equals 3. Okay, so we want to find the area underneath this graph between 0 and 3. Let's sketch this graph. And it's just going to be a sketch, it's not going to be anything exact. So it looks something like that. Because a negative quadratic, so you could think of this as the t squared graph, but then the negative t squared graph, so it's an N shape rather than a U shape, stretched by 2, and then moved up by 4. In terms of its roots, 4 minus 2t squared equals 0. So that'd be 4 equals 2t squared. So 2 is t squared. So t is plus or minus root 2. And root 2 is about 1.4. So I'm going to label that on here 1.4 and minus 1.4. Now we've got to find the distance covered between t equals 0 and t equals 3. So it's not even on my graph, is it? Let's extend this graph down a bit. And we're just going to put 3 here. I know it's not ready to scale, but that's fine for now. So we want to find this area here between 0 and 3. Okay, that's the area that we need to find. Now you can notice that some of it's going to be positive and some of it's going to be negative. If they asked for the displacement, then that would just be the integral between 0 and 3. So it would be this area minus this area. So that would be like your net area, would be your displacement. because displacement is a vector. However, we've been asked just for the distance, so what we want is just the raw area. We don't care about if it's negative or positive, we just want to know how much area in total is there, how much distance in total has been covered. So what we're going to have to do is split it up into two different integrals. So we're going to first of all integrate between 0 and root 2, or 1.4, to find the positive bit, and then we're going to integrate between root 2 and 3 to do the negative bit, and then add them together, but use the positive version of both. So we're going to have to integrate 4 minus 2t squared between 0 and root 2 with respect to t. I'm actually going to do that on my calculator because we know how to integrate from pure maths, so that's fine. I'll show you how to type in this integral on your calculator. So this is just on the scientific one, so you can use this integral button at the top. And we had to integrate 4 minus 2t squared, so 4 minus 2, and then for x, you can use this red x here, so you have to do alpha on that one, squared. Now it's between 0 and root 2 as my first one. So if I do that, 3.771. Okay. And then we need to do it again. So the same thing, but we're going to go between root 2 and 3 for the same function. Maybe I'll show you how to do this one on the other calculator now. So on the graphics one, if we go into, if we press math, and then on the next page there's an integral button, and then we do the same sort of thing. So our expression was 4 minus 2t squared, 4 minus 2, and then for x you can just use this button here, squared. This time it's got to be between root 2 and 3. I'm going to do minus 9.771. Okay. So that's as expected. We've got one positive area, one negative area. So the total area is going to be 3.771 plus 9.771. So it gives me 13.542 meters, and that is the total distance. If they wanted the total displacement, so basically where is the particle after 3 seconds, then that would be 3.771 minus 9.771. So that'd be like the net area. So just go careful. 1, are they asking for distance or are they asking for displacement? And 2, draw a graph just to check, is there going to be a negative area? Because if you hadn't drawn a graph, you might have just gone straight to doing the integral between 0 and 3, in which case you would have got 3.771 minus 9.771, and you wouldn't have realized that actually part of that was a negative area. Okay, you should now be able to have a go at exercise 11D if you want to, which is on using integration. But what we're going to go on to next is doing a mixture of some integrating and some differentiating. So if you wanted to leave exercise 11D and just do the ones of a mixture, then that's fine. Okay, in this example then, the velocity of a particle after t seconds is v equals 6t minus t. After 5 seconds, the displacement is 75 meters. Find an expression for the displacement. So we've got velocity, we want displacement. Displacement is the integral of velocity, so the area under a vt graph. So we need to integrate this. So it's going to be 6t squared over 2, so that'll be 3t squared minus 2t. We need to do plus c as well. To work out c, use the extra information they've given us. So they told us that when t is 5, the displacement is 75. So we can substitute that in. So that's 3 lots of 5 squared minus 2 lots of 5 plus c, and that should give me 75. And now I can solve this to find c. So c is going to be 10. So my full expression for s is going to be 3t squared minus 2t plus 10. For part B, find the displacement after 10 seconds. So I can use this expression I've just got and plug in 10. Okay, and I can see what I've got. So it's going to be 3 times 100 minus 20 plus 10. So that's 290 meters would be my displacement. Okay, this next one, this is a past exam question. So a particle P moves on the x-axis. The velocity of P at time t is given by this equation here. 2t squared minus 9t plus 4. We know that when t is 0, the particle is 15 meters from the origin, so s equals 15. We've got to work out the values of t when it is instantaneously at rest. So that means the velocity is 0. So we can set this quadratic equal to 0. And then we can solve it to find t. So I'm just going to do that on my calculator. So my two values of t are 4 or 0.5. For part B, the acceleration when t is 5. So we've got velocity. To get to acceleration, acceleration is the rate of change of velocity. So dv by dt is going to give me the acceleration. So I need to differentiate this expression. So that'd be 4t minus 9. And then I want to find the acceleration when t is 5. So a is going to be 4 lots of 5 minus 9, which is 11 meters per second squared. Part C, the total distance travelled between 0 and 5. Well, we'd better check what this graph looks like. So I'm going to sketch the VT graph. Okay. Now we've already got its roots because we solved where it equals 0 before, so that's quite useful. So it crosses the x-axis, or I suppose we should call it the t-axis in this case because this is time, at 0.5 and at 4. And it's a positive quadratic. So it looks a bit like that. Okay, there's my graph. And we want the distance travelled, so the area under the graph, between 0 and 5. So that's going to be this area here, plus this area here. And then 5 is obviously further along than 4. So it's also going to be plus that one there. So I've actually got 3 different sections of area that I need to work out. So the first one would be the integral of 2t squared minus 9t plus 4 dt, because remember, displacement is the integral of velocity, the area under a VT graph. My first limit is going to be between 0 and 0.5. Now my second section is going to be the same thing. Let's try this a couple of times. Now my next one, rather than between 0 and 0.5, it's going to be between 0.5 and 4. And then the last section is going to be between 4 and 5. Now, you can work these out by hand, but you can use your calculator too, and you can do that in an exam as well. If it's just a numerical piece of integration, then you can just do it on your calculator, unless the question says something like you must show all your working, or solutions using calculator technology will not be allowed, something which alludes to the fact you can't just do it by calculator and you've got to show a bit more thorough working. But unless it says something like that, then you can just plug it into your calculator and find those 3 areas, which is what I'm going to do now. So I've just gone through and calculated all those on my calculator. So the first area is 23 over 24. This negative one is minus 343 over 24. And this positive one is 25 over 6. So total area, which is the total distance, is going to be 23 over 24 plus 343 over 24 plus 25 over 6. And I can find the total of all of those. And that gives me 233 over 12, or as a decimal, that is 19.4 meters. That would be my final answer. Okay. And again, just be careful. Is it asking you for the distance or is it asking for the displacement? Because if it said the displacement, then it would matter that some bits were negative. So if it was the displacement, I would do this area, subtract this area, plus this area. But in this question, it just asks for the distance. So we can just do the total areas all added together. Okay, here's another exam question. So particle moves with a velocity given by 12 minus 2t squared. This is velocity. Find the distance travelled in the first second. So again, I think I'm going to draw just a quick graph of what this looks like. So 12 minus 2t squared equals 0. I'm just going to try and find the roots quickly. So give me 6 equals t squared. So t would be plus or minus root 6, which is 2.44. Okay, so there, which is root 6. And it's a negative quadratic, so it looks a bit like that. And this point here would obviously be 12. The distance travelled in the first second, well, root 6 was 2.44. So that's well within the positive bit. So I don't have to worry about doing two different areas here, okay, because it's just a positive bit. But in the first second, so this is between t equals 0 and t equals 1. That's the first second, so 0 to 1. So I'm going to integrate to find the distance, 12 minus 2t squared between 0 and 1. I'm just going to do that on my calculator. And I get 34 over 3, or 11 and a third, or 11.3 recurring. Part B, the value of t when p changes direction of motion. So that is when the velocity goes from positive to negative, a bit like on these other questions we talked about where it follows an arc and it's going upwards and then it's going downwards, while the point where it changes direction is going to be that bit there where the velocity is 0. It's going from a positive velocity to a negative velocity, or vice versa. So we want to find when velocity is 0. So we've already got an expression for v. So 0 is 12 minus 2t squared. And in fact, we solved this earlier. T is going to be root 6, or that is 2.44 seconds. For part C, the value of t at the instant p returns to its starting point. So we want to find when is its displacement 0. So let's find an equation just for its displacement first of all. So displacement is the integral of the velocity. So we need to integrate the velocity. So that would be 12t minus 2/3 of t cubed plus c. Now, it doesn't give us any information about where it starts, so I think we can just assume that it starts at the origin and then calculate when does it return to the origin. Okay, so we're not going to include plus c, we're just going to make that plus 0. And we're going to find when does it go back to the origin, so when does it go back to displacement 0. Okay, so to solve this equation, I can factor out a t, like that. So my first solution is t equals 0. Well, that's obviously the first time it's at the origin, at the start. It starts at the origin, so that's easy. And the second solution will be when this bracket equals 0. So I'd have 12 equals 2/3 t squared, because I start with 12 minus 2/3 t squared. Maybe let's write that. 2/3 t squared equals 0. Solve that to here. So 12 times 3 divided by 2, and square root it. So that gives me 3 root 2. If they want an exact answer, or if they want as a decimal, 4.24 seconds is how long it takes to go back to its starting position. Okay, last one. The displacement of a particle from the origin after t seconds is given by s equals t squared times t plus k meters. And given that p is at instantaneous rest when t equals 4, find the acceleration when t equals 10. So it feels like giving us quite a different set of information here, but let's write down what we know. So we know the displacement, rather than s, I'm going to use x, I think. So the displacement is given by t squared t plus k. Or I suppose we could write that as t cubed plus k t squared if we wanted to. We're also told that it's at instantaneous rest when t is 4. So we also know that when t is 4, v is 0. Okay, that's like a coordinate that we've got. When t is 4, v is instantaneous rest, so it's 0. And we've got to try and find the acceleration. Well, the first thing we can work out, we can go from displacement to velocity by differentiating. So dx by dt, so the rate of change of displacement is your velocity. So I'm going to differentiate this. That'll give me 3t squared plus 2kt. So that's my expression for velocity. And now I know that when v is 0, t is 4, or vice versa. So that would mean that 0 equals 3 times 4 squared plus 2k times 4. So that would be at 3 times 16, which is 48. And this is plus 8k. So that means that k is 48 divided by minus 8, which is minus 6. Okay, so really I know that my full equation for velocity is 3t squared, and that's 2kt, so that's going to be minus 12t. That's my equation for velocity, now that I know k. And the last part of the question, find the acceleration when t is 10. Well, the acceleration is dv by dt, the rate of change of velocity. So I'm going to differentiate this, so that'll be 6t minus 12, and then we want it when t is 10, so you can substitute that in. So that's 60 minus 12, which is 48 meters per second squared, would be my final answer there. So hopefully you can see that this is a really useful tool to be able to use calculus and relate all those things that you learn in pure into an applied concept in mechanics. If you wanted to, you could actually apply calculus to the constant acceleration problems that we had in chapter 9, if you knew the equation of the line. But it's just that when we're dealing with constant acceleration, it's actually a bit easier to just use those Suvat formulae. But you could if you wanted to. Okay. So the key thing to remember is if it's a constant acceleration, you can use Suvat. If it is not constant acceleration, you can use calculus, so differentiation and integration. Now, in terms of questions, you can either have a go at mixed exercise 11, or I've also got three other sets of questions here actually. It's basically some leveled questions on this topic with a mixture of integration and differentiation, because that's the real skill, is picking when to do which one. So you've got level 1, which has got some questions, level 2, which has got some questions, and level 3 as well. And I've also included some work solutions too. Okay, so not just the answers, but the solutions as well, just like the textbook has. So you can pick what you want to do. You could start at whichever level you want to. Level 3 is definitely quite hard, but you can start at whichever level you want to on those questions.